Hi, I'm Lil Ophie, a tutor for Memphis Community University, and today is a very exciting day because we are practicing U-subs. Now, U-substitution allows us to find the antiderivative of a composition of functions, like how the chain rule allows us to take the derivative of functions within functions. So while you might know the power rule or have memorized antiderivatives for special functions or can take the antiderivative of sums and differences, U-substitution really expands the amount of antiderivatives that we can find. Unfortunately, U-subs are a bit more difficult to use than their counterpart, the chain rule. So before we go over any examples, let's discuss the steps of a U-sub question. Now, the purpose of U-subs is to convert a more difficult integrand containing x's to an easier integrand containing u's by utilizing certain relationships between u's and x's. Remember that U-subs are the opposite of the chain rule and are used for a composition of functions. So we start by designating an inside function as u. And this first step of choosing u is probably the trickiest step, so we'll go over it in more depth later. But for now, we'll choose functions that are within other functions, and in this case, c times f of x is within g prime of x. So with the first step of choosing a u done, our next step will be to take a derivative of u with respect to x. And because our ultimate goal is to get equations relating u's with x's, we're going to move over the denominator of dx to the other side of the equation so that we get du equals c times f prime of x times dx. Keep in mind that this is how we're going to approach our derivative steps going forward, where it will be du equals the derivative times dx. And it'll be helpful to isolate our x's when we change them to u's. So I like to bring over any constant that might be on the x side of the equation. And we'll get du over that constant equals our derivative times dx. Now with our equations prepped, we're ready for the key step of changing all of our x's into u's, and we're going to do that in two stages. Within our outside function, we're going to substitute c times f of x with u, since c times f of x is equal to u. So our new integrand will begin with g prime of u, but we still have some x's that need to be replaced, mainly f prime of x times dx. But we already solved for exactly f prime of x times dx earlier, as du over c is f prime of x times dx. So we're going to sub in du over c not just for f prime and not just for dx, but all of f prime of x times dx combined. And notice that we now have a way easier integral with no x's and just u's. We might as well bring that constant out of the integral before our antiderivative. And at this point, we should be ready to take an antiderivative since our new integrand with u will be way simpler than our original integrand with x's. So we'll take the antiderivative of our new integrand, so we'll get 1 over c times g of u plus c. And for our final step, we're going to resub back in our choice of u so that our final answer contains x's like our original question. And those are all the steps of a u-sub. Before we get to our examples, as promised, I want to give you some hints on our first step of choosing u, since if you mess that up, you mess up the entire problem. Since u-subs are used to take the antiderivative of a composition of functions, our choice of u should be functions that are within other functions. So we'll choose for our u functions that are within parentheses, square roots, exponents, denominators, etc. So for these three example integrals, we'll choose sine of x as our u, since sine of x is inside other functions. But for extra tricky questions, even with our first hint, we still might struggle choosing u. So the best way to identify what functions should be our u is to find functions whose derivatives are also a part of the integrand up to a constant. And what do I mean by that? If we take the following example, remembering that the derivative of tangent x is secant squared x, we should choose tangent x as our u, so that secant squared x will be part of the du. And similarly, for this integrand, since the derivative of ln of x is 1 over x, which is also in the question, we'll choose ln of x as our u. But our exact derivative of u doesn't have to all be in our original question, as long as the x's perfectly match. So I argue that for this example, x squared plus 2x will be our best candidate for u, because while its derivative 2x plus 2, which is equivalent to 2 times x plus 1, isn't verbatim in our original integrand, notice that if you ignore the constant 2, all of the x's of x plus 1 times dx are there in the original question, which is why we choose x squared plus 2x as our u in the first place. I know this is a lot to take in, but we're going to slowly carry out this long u-sub process for these 5 examples in this video. Let's get u-subbing. Example 1. Our first u-sub is going to be the integral of x squared times cosine of x cubed. Let's slowly follow our u-sub process. First, we have to choose a u, and the best candidate is x cubed. Since x cubed is inside another function, cosine, and its derivative, 3x squared, is also a part of the integrand besides the constant. So now that we have chosen a u as x cubed, we take the derivative and always bring over dx, so du equals 3x squared times dx. And I like to try and isolate just the x's, so let's go ahead and divide this by 3. So we have du over 3 equals x squared times dx. So now we're going to substitute every x in our original integral with u's. We will start with our same outside function of cosine, but inside cosine we're going to replace x cubed with u. So we'll have cosine of u. And now we have to replace those remaining x's in our original integrand, which is a combo of x squared times dx. But we've already solved for that exact combo of x squared times dx, so we're going to substitute d over 3 for all of x squared times dx in one single action. Notice that we've accomplished our first goal of changing all the x's to u's. Bringing our constant out of the integral will make our next goal of taking the antiderivative easier, so let's take out 1/3. At this point, we should know the antiderivative of the remaining integral, and thankfully we know that the antiderivative of cosine is sine, so we'll have 1/3 times sine of u plus c. And our final step is to stub back in x's for u, and since u is equal to x cubed, our final answer is 1/3 sine of x cubed plus c. So while doing a u-sub is more involved than taking a derivative with the chain rule, hopefully you have a better sense of each step of this process. Example 2. Let's keep it rolling with our next u-sub example of 2 over 5x plus 1 to the 4th power. Starting our u-sub process, 5x plus 1 is our obvious choice for u since it is within the parentheses of another function. So we'll let u be 5x plus 1. And du will then just be 5 dx. But even if our only remaining x is dx, I still prefer to isolate it, so we're going to bring over the 5. Thus, du over 5 will be dx. Let's change all the x's into u's in 2 steps just like last time. Keeping our 2 over something to the power of 4 intact, we make our first change of x's for u's by replacing 5x plus 1 with u, since that's what we chose for u. So our integrand becomes 2 over u to the 4th power. And now the only remaining x is dx, which we solved for earlier. So we're going to replace that with du over 5, with no more x's. Let's take out our entire constant out of the integral, which is 2 over 5. And before we go for the antiderivative, let's rewrite our integrand as u to the power of -4, so that we can use the power rule for this antiderivative. To start the antiderivative, we keep our original constant of 2/5 in the front, and then to use the power rule, we add 1 to our old power of -4 to get a new power of -3, and then we divide that new power of -3, so that our final antiderivative will be 2/5 times -1/3 times u to the power of -3. And we can simplify these constants so that they will become -2 over 15. And to finish, we don't forget to replace our u with 5x plus 1 from the very beginning of the problem. If you want, you can change our answer to look like our original question by changing our negative exponent back into a fraction. So our final answer is -2 over 15 times 5x plus 1 cubed plus c. So be wary of these sorts of u-subs where our choice for u will be a linear function, as they appear a lot. Example 3. For our next u-sub example, we're going to be taking the antiderivative of this fraction. So let's start u-subbing. Here we're going to let our u be the denominator. While it doesn't look like this function is inside another function like our previous choices for u's, it actually is, as it is the denominator of this fraction. But the main reason we choose the denominator as our u is because the numerator is the derivative of the denominator up to a constant. So by letting u be x cubed minus 3x squared plus 9x minus 1, du will then be 3x squared minus 6x plus 9 times dx. And notice that we can factor a 3 out of each term within this parenthetical, so du will be 3 times the quantity x squared minus 2x plus 3 times dx. And let's isolate our x's like normal, so let's divide by this 3 that we just factored out, so du over 3 will be x squared minus 2x plus 3 times dx. And now for the key step of changing our x's to u's. No matter what, our integrand will still remain a fraction, so let's rewrite our fraction bar. And we chose the denominator as our u, so let's make u our new denominator. We still, though, have a bunch of x's to replace, the entire numerator and dx itself. But notice that these x's all together are exactly what we found earlier to be equal to du over 3. And this isn't a coincidence. If you're doing a u-sub correctly, the remaining x's, crucially including the dx, after you sub in u, will be exactly those x's from that step. So for this particular question, in one fell swoop, let's replace all of x squared minus 2x plus 3 times dx with du over 3. With this much simpler integrand, like normal, we're going to take out our constant of 1/3. So we will now be taking the antiderivative of 1/3 times 1 over u times du. And famously, the antiderivative of 1 over u is ln, so our antiderivative is 1/3 ln of the absolute value of u. And finally, we replace our u with the original denominator. So our final antiderivative is 1/3 ln of the absolute value of x cubed minus 3x squared plus 9x minus 1 plus c. Hopefully you're starting to get familiar with the u-sub process. Choose u, then find du, change all of our x's into u's, take the antiderivative, and then sub back for u. All right, example number 4. For our next example, we're going to be tackling a classic u-substitution, as we will be taking the antiderivative of tangent of x. But there doesn't seem to be any sort of composition of functions here, so we have to modify tangent of x in some way to introduce a composition of functions. To do so, we're going to use the famous trig identity that tangent x is sine x over cosine x. But as we go for our u-sub, it's not obvious whether u should be sine x or cosine x, as they're basically derivatives of each other. Sometimes in math, it's useful to see how a process might go wrong. With that in mind, let's choose sine of x as our u. So then du would be cosine of x times dx, and with the x's already isolated and no constant needing to be brought over, we can proceed with changing our x's to u's. So we'll start with our fraction bar, and our choice of u being sine of x means u will go into the numerator. But now we need to replace dx over cosine x, but we isolated cosine x times dx, so we've hit an impasse as we have no way of properly changing the rest of these x's into u's. But worry not, we got stuck since we chose the wrong u in the first place. But if you go to the very beginning and choose cosine of x for our u instead, then du will be negative sine of x times dx. And let's isolate sine of x times dx, so we'll bring over this negative. So negative du will be sine x times dx. And now let's see if we chose the right u this time. We'll start with our fraction bar. And since we chose cosine for our u, and cosine is originally in the denominator for our integrand, u will go into the denominator of our new integrand. The rest of the x's that need to be replaced are sine x times dx. And unlike our wrong choice of u, sine x times dx is exactly equal to negative du. So this time we're able to change the rest of our x's into u's as we change all of sine x dx into negative du. We might as well take out the negative sign out of the integral. So we're ready for our antiderivative now, and we actually have the same antiderivative as last time, so it will be negative ln of u. And for our final step, we plug back in cosine for u. So our final answer is negative ln of the absolute value of cosine x plus c. It's very common to choose a wrong u when starting out with u-subs, so don't hesitate to go back and choose a new u in the case that you get stuck. Example 5. Our last example will be our most challenging, as we're going to try to find the integral of secant squared of the square root of x divided by the square root of x. Like the last question, while it's not entirely necessary, if we rewrite our integrand, this time by using fractional exponents for these square roots, with the bottom square root being written as x to the negative 1/2 since it's in the denominator, it will be easier later on to choose our u and change our x's into u's. Written in this form, hopefully it makes sense that x to the power of 1/2 should be our u, since it's inside another function of secant squared. And its derivative, x to the negative 1/2 power, is also in the integrand, up to a constant, of course. So with x to the 1/2 power being our u, then by the power rule, du will be 1/2 times x to the negative 1/2. And this time, to isolate our x's, we'll have to bring over this constant as 1/2. So unlike all of our other questions, we'll lose a fraction, and 2 du will be x to the negative 1/2 times dx. Changing all of our x's into u's one final time, our secant squared will remain, but instead of x to the 1/2, we will put u within secant squared. So we'll have secant squared of u, and we found earlier that the remaining x's of x to the negative 1/2 power times dx exactly equal 2 du. So we will replace all of the x to the negative 1/2 power times dx with 2 du. After taking out our constant of 2 out of the integral, we can take an antiderivative, and our antiderivative of secant squared of u is tangent u. Of course, our answer needs to be put in terms of x's, so subbing back in, our answer will be 2 tangent of x to the 1/2 power. And for the sake of simplification, let's change x to the 1/2 power back to a square root, so our final answer is 2 tangent of the square root of x plus c. And that's how you U-sub. Be sure to subscribe and check out our other integral videos on our channel. We have videos on definite U-subs where we have to deal with plugging in numbers, and videos where we skip the entire U-sub process for easier antiderivatives. We also have videos on other integration methods like parts and partial fraction decomposition if you need help with those methods. Until then, thanks for watching, and I wish you well on your U-sub journey. Thank you.